So, bad start. Anyway, so welcome very much for the Nano Innovation Award 2020. Somehow the microphone, which worked just 15 minutes ago, didn't work anymore. So I'm the Dieter Braun, spokesperson of the Center for Nanoscience. I welcome you all here in our nice lecture hall. So due to Corona, we have to do it with distance. So we try to keep it as much as possible. And unfortunately, we also won't have the Sommerfest, which is always the great thing after the end of semester. You meet your colleagues again, drink a beer. So unfortunately, you probably have to drink the beer alone, or perhaps you have some scientists around you. So today, I welcome to you also Joachim Rädler from CENS, who's part of the jury for the NanoScience Nano Innovation Award, and Khaled Karai, attocube system, also jury member. And what we'll do today is that we honor outstanding innovative PhD theses in application-oriented nanoscience. We do this since 2015, where we award this prize through CENS and by the very generous input, financial input from our older spin-offs, in the hope that the PhD theses of today will be the spin-offs of tomorrow, the taxpayer of tomorrow after, and giving us funding opportunities in the future too. So unfortunately, also this year we couldn't invite people to Venice, which is a typical thing to honor the prize awardees. So, you know, our background is almost Italy. Well, it's Greece, okay. So we try to get as close as possible to our Venice experience. Last week we had the CENS Meets Industry on a very nice virtual platform. I think it will be the future. So Corona is teaching us how to do things a little bit in larger distance. And we'll do a lot to do that in the future. So what we will give to 3 awardees today is a total prize money of €7,500 spent by attocube, Nanion, and NanoTemper. And this is where Khaled comes in to explain a little bit the motivation for this prize. Please.
Thanks, Dieter. As you introduced it already, this sponsor is financed by 3 companies. All 3 companies actually were founded in CENS. They grew out of this very special blend that CENS was and is today, which is this blend between top science in nanoscience and technology application. And at that time, at the foundation part, the companies came a bit like spontaneously, and they were successful. And the 3 of us, attocube, Nanion, NanoTemper, felt, well, we have to extend our thank you to CENS and also help the next generation to follow steps by putting some sponsoring behind that. So this is in line keeping the tradition alive, to stimulate startup culture, to stimulate innovation, of course, stimulate career, but also stimulate the discourse between industry and science, I think, which is really the way to the future. And you just mentioned that the prize, the NanoScience Award of CENS, is since 2015. It had its roots slightly before, started with attocube, and back then we established the aspect innovation. So there are many good science prizes, and we wanted to insist on the innovation part. And innovation was about transmission between, a good scientific idea, but also with an application background. And the jury had as a mission 5 criteria to look at. First, the validation of the idea. Is there a solid model or simulation or a prototype behind that, a proof of its existence? Number 2, that needed to be peer-reviewed, scientifically speaking. So the paper, the accepted paper is essentially an important part. It needs to be application-oriented, of course. So somewhat of a demonstration of the application of the idea behind it. And the plausibility of the application also makes a big part of it. Is someone else convinced about that? And the last one is the innovation quality. Very difficult to establish, But in the end, innovation is when you say, wow. Okay.
That sounds a good criterion. So we opened this prize since 2017 to whole Bavaria, and we actually received this time 18 applications from LMU, TU, Max Planck, VU Erlangen, University Augsburg, University Würzburg. And it was a two-stage selection process. Basically, there's a pre-selection, but then the finalists, based on written evaluation and selection, were selected to, this time, 3 winners by a jury meeting. So the jury was Angelika Vollmar from KUB LMU, Hubert Krenner, Physics University Augsburg, Khalid Karai, Scientific Director of attocube, Jens Riegler, Research Consultant, and Joachim Rädler from Physics LMU. And I was told that quite a number of awardees, or who applied for, has made really nice movies, but that's up to you to introduce.
Yeah, actually, not much to say about that, other than it was very difficult, but the last 8 basically nominees made really wonderful movies, and 1 minute, I think, and we will now watch the 8 presentation.
These are our awardees, please.
What we see here, you might think nothing. Actually, we look at something worth Nobel Prize. Efficient wildlife emission. To be precise,
and then we understand the model better. For example, a trained neural network distinguished numerically simulated pictures from 2 competing theories. After training, I showed the neural network about to finish my PhD in physics at the group of Professor Franz Pfeiffer. My research project is the nanosciences. The nanosciences is basically an X-ray microscope with which you can solve structures bound by nanometers. This is one of our implementation examples for our chemical project. Chemical histology, and what exists is that microscopy of cell biopsies. The conventional techniques and the nanosciences
They resemble tiny antennas, but instead of switching the radio channel, they switch their color. My goal was to connect these antennas and build complex networks. The radio channel lies in the fabrication of these structures. They are extremely small, just so you know. They are indeed so small that on this scale, the commonly used method is too rough and grainy. It's just like you were cutting out something from polystyrene. I was able to significantly improve the synthesis of both silicons to show perfect atomic order. They can now be used for large arrays of extremely accurate structures. This material allowed me to develop a spin-off in nano devices, and I'm now working on applications in the commercial biosector.
Hi, my name is Lilian, and I want to present to you the innovation and application of my work. This is a pregnancy test. I got it from the drugstore. Why do I want to know if I have the HI virus? Why does the drugstore not provide tests for virus infection? Why do I have to go to the doctor where it's full of sick people and where I have to spend my time waiting? The reason is that these strips are yet not sensitive enough. Sick people have only picomolar amounts of viruses. That's why it's not easy to apply these test strips. The core ingredient in these strips are gold nanoparticles. We exchange them by much better particles, gold, silver, Crucial nanorods, to reach higher sensitivity. Our goal is to bring diagnostics to your living room.
Hi, I'm Anka, and I did my PhD in Joachim Reh's group on analyzing single-cell hypothesis of mRNA transcription kinetic. Or to put it simply, I use single cells as test tubes to observe how artificial mRNA encoded for CFP is delivered into the cells, which start expressing the fluorescent protein. For mRNA delivery, I used it with nanoparticles and studied how they are uptaken by the cell. In order to do this in a standardized manner, the cell is confined to a microcircuit diffusion spot. After mRNA delivery, the cell produces GFP over time. This expression kinetic can be measured by time-based microscopy, and the kinetic parameters of this translation process can be analyzed. Looking at one single cell is not that informative, of course. That's why I arranged thousands of cells on an array allowing for live cell imaging to study cellular kinetics, a method called LISCA. With LISCA, it's possible to study the influence of nanoparticles on cells over time to obtain quantitative information based on single cell arrays, as shown in this snapshot.
During my PhD in the lab of Bavarian, I worked on advancing applying DNA-based super-resolution microscopy. Here I worked on pushing the resolution limit down to a localization position of 1 nanometer. We demonstrated this on DNA origami nanostructures. In combination with more binders, we showed that we can resolve individual proteins of the nuclear core complex in cells spaced 12 nanometers apart from each other. Additionally, I worked on increasing the speed of the super-resolution technique DNA paint to enable high-throughput spatial omics experiments for biomedical applications. In order to demonstrate this, we did large field super-resolution imaging. So this is the 4x4 micrometer image of cellular microtubule filaments, now zooming out to a 100x 100 micrometer image. And finally, here's the square millimeter DNA paint image with a resolution of 20 nanometer, acquired in only 8 hours.
Excellent, fantastic. So you've just seen the 8 finalists of this year's Nano Innovation Award. Thanks to all of you for presenting in such exciting films. That's unfortunately the way we have to do it during Corona times. I wished you could all be here. I also like to thank all applicants. We had 18 applications this year from a broad range of subjects, from nanobioscience all the way to quantum sciences. To me, it's absolutely amazing to see how much enthusiasm, hard work, excellent publications, and how much smart ideas we've seen in the applications. So the decision was hard. And it's now my pleasure to announce the winners. In the name of the jury and the Center for Nanoscience, the winner is, please, the third prize of the Nano Innovation Award 2020 goes to Enno Kraus. Please. Enno Kraus comes from Würzburg, from the group of Professor Bert Hecht. He developed a clever method to optimize the manufacturing of single crystal gold platelets. This allows to produce extremely precise arrays of gold wires, and due to the high precision, previously overlooked signaling pathways could be examined. As an example, he developed a plasmonic circuit which is able to sort photons according to their helicity, and to emit photons in a spatially separated position. This is the same, basically, as spin optics devices, as the analog to spin electronic devices for electrons. The results could open up a broad range of future applications in nanophotonics and new applications in quantum information processes. So in fact, together with his colleagues, Dr. Henriette Maas and Dr. Tien An Le, Enno Kraus recently received an EXIST grant for a startup company called NanoStruct to bring his ideas into commercial applications in large-scale production of homogeneous metallic nanostructures. Good luck with this. Taken together, the jury was convinced and impressed by his elegant method, as well as his effort to commercialize his ideas. Congratulations. Let's go for... Okay, thank you very much. And you have the opportunity now to present your work in more detail than I could do now. Please.
Okay, so once again, I want to thank the jury for this decision. I'm totally excited about this, especially given the field of extremely good competitors. And thank you very much. So I want to give a small introduction about my talk. My talk is about nano-optics with single crystalline gold platelets. And I want to start with, one can maybe even say, the starting of nanoscience. It's a visionary talk, plenty of room at the button, given by Richard Feynman in 1959 at the Caltech. And he there envisioned that when our basic technological building blocks get smaller and smaller, they not only get changed quantitatively, but also can express completely new features. For example, he mentions that when computers get more complex and even more complex, at the end they will be faster, but they also will be able to do completely new things, like, for example, recognize faces or make their own decisions. This is strikingly up to date, and if you think about it, he said this 60 years ago. So he also mentions there already antennas. Is it possible, for example, to emit light from a whole set of antennas, like we emit radio waves? So is this possible? Well, basically an antenna is a resonator for electromagnetic waves. And the smaller the antenna gets, the smaller the wavelength for which is resonant will be. So you basically just need to do the antenna small enough. If we now look at the scale, for radio waves we have wavelengths ranging from kilometers to meters. If we now get smaller to the microwave regime, we basically have something where we heat our food with, the microwaves. And if we now get even smaller, a few hundred nanometers only, then we have the part of the electromagnetic spectrum that we call the light. So you basically just need to make your antenna nano size. And this can be done. Here's a picture of such an antenna, and in the middle you can see an optical scattering of these antennas, and from the bottom to the top they get longer, they change their resonance, and as you can see, they change their color. And those antennas have fascinating applications. They can enhance signals, but not from a radio program, but from single molecules. This is extremely interesting for biosensing. But they can also, my work was about to connect these antennas to complex networks, which are smaller than optical diffraction limit normally allows it, but they are still as fast as light. They are really well suited for ultra-phase data transfer on chips. However, as Feynman mentioned, there also arise new possibilities, and that is that a photon carries a quantum information, a spin, and those devices can thus be used for quantum computing as they carry this information. So, the challenge lies in the fabrication of these structures. If we want to get an impression how accurate you want to be, I want to bring again the picture of the zoom-in from my movie, and I will now further zoom in into this structure. And as you can see in this last picture, you already start to see stripes. And those stripes and dots are already the atomic lattice of the structure. So the distance between two atoms. And this gives you an impression of just how accurate you need to be in fabricating these structures. And this is actually not only a fabricating problem, but also, again, a problem from the starting material, because common metal is rough and grainy on the nanoscale. This is something already Feynman mentioned in his talk 60 years ago. The metals that we use have a grain structure, and this would be very annoying at small scale because the material is not homogeneous. When we now use a structuring method, like in this case focused ion beam milling, to build such a structure out of common metal films, you can see that they are quite rough and not really homogeneous. And this is really inherent to the starting material we use for our structuring. The solution lies in using atomically well-defined starting materials, so single crystals, metallic single crystals. And if I use the same structuring for such a single crystal, I can see that the structure is way more accurate and way more homogeneous. So to build such extended optical networks out of it, so really bigger structures, we need that these crystals are at the same time extremely flat, so only a few hundred atoms, on the other hand, laterally really extended over as much as possible, hundreds of microns. And I was able to significantly improve the synthesis of these gold single crystals so that they are now below 20 nanometers thick, while at the same time they can reach lateral extensions of up to 0.2 millimeters. At the same time, the synthesis was facilitated, so it's now very cost efficient and scalable, and I also developed a method to automatically determine their thickness in a very fast way. I then investigated whether this material was capable of supporting a large amount of structures with a high accuracy, and I fabricated hundreds of structures and measured them and was able to achieve an unprecedented reproducibility for these kind of structures. So then with that I was able to show that they are really able to be used for such optical networks. And then, with this material at hand, designed a device that can be the building block of optical quantum networks. It's basically a plasmonical optical waveguide where we can incouple photons and those photons are then laterally sorted in this device according to the helicity or spin. And what is even more important, at the end of the structure, they are re-emitted in their initial state. And this is a crucial part if you think about implementing this building block into a larger network, because you want to keep this quantum information. So with the gold platelets as a very exact material at hand, I was able to directly and very accurately reproduce the geometrical dimensions obtained by numerical simulations, and was then able in optical measurements to confirm that the device is working. So you can basically see here an excitation with one or the other helicity, and you can see that the signal switches from one side of the device to the other of the device. So while quantum computation is an extremely interesting topic, commercial applications in the near future are probably not given. However, those structures have commercial applications, and actually those applications face the same problem that I faced for my optical networks. Homogeneity, reproducibility, and accuracy for the nanostructures over a large area. So, as an example for application, I want to give surface-enhanced Raman scattering. Here, the Raman signal is basically a signal like a fingerprint which can identify a molecule. So it's very accurate, however, the signal is very weak. Plasmonic antennas can enhance the signals by billions of times, thus boosting the efficiency of this sensing method by orders of magnitude. It has powerful applications. For example, you can detect viruses or explosives with it, or you can use it in drug development. However, the common materials used for this are not reproducible. They always give a different signal or a different enhancement originating from the different shape of the antennas, and this is not very good for commercial application. To basically give a solution to this problem, I want to use my gold platelets, but together with a structuring method. This allows me to really fabricate structures in a commercially reasonable way, and this is why I basically invented a special kind of parallel structuring, a nano imprint lithography process adapted to the crystals, which allows the structuring of those of the gold crystals in a very fast and scalable way. This project is now with my team NanoStruct is funded by the program, and I hope that with that in the future I will be able to bring my nanostructures into many different fields with high social and economical benefits. So, and with that I want to thank the jury again for their decision. I want to thank you all for listening, and I also want to thank, of course, all the people that helped me with my work. First of all, my supervisor Bert Hecht, the whole nano optics group in Würzburg. I want to highlight Dr. Thorsten Feichtner, Sven Großmann, and Maximilian Ochs for contributing pictures to this talk, and of course all the others I worked with, and also my current team from NanoStruct, Dr. Henriette Maas, Dr. Tianan Lee, and Kai Leibfried. Thank you very much.
Thank you.
So the pressure is going up. So I have the immense pleasure to announce the second prize. And this will be given to Lynn Nguyen. Lynn is unfortunately today sick at home, I understand. I hope she's watching us. She'll be represented by her advisor, Dr. Amelie Hoyer-Jungmann. I will quickly read the laudatio that the jury came up with. So Lynn, from the group of Professor Tim Liedl at the LMU, came up with an ingenious but simple idea of a one-pot reaction to synthesize highly stable silver nanorods and nanoparticle coated with a wide range of hydrophilic anchor groups, including DNA. Her method solves a long-standing problem that, so far, silver nanoparticles with any coating degraded in aqueous environment, in water environment. Silver is an excellent material for plasmonic studies and applications. Her solution open a wide range of possible applications, for instance, in diagnostics, that we need very dearly right now with COVID. Lynn was able to produce impressive results with lateral flow assays where her silver-coated particle provide higher detection sensitivity than standard gold nanoparticle, and they are stable. Lynn has published her work successfully and also filed a patent application. Together with Maximilian Urban, she pursuing the foundation of a company, and the team was recently invited to present their idea at the pitch day of the Medical Valley Award. The Nano Innovation Award aims not only at distinguishing the achievement of Lynn along all the line of the award's evaluation criteria, it also meant as an encouragement for her endeavor toward the commercialization of her innovative approach. Congratulations, Lynn. So we will hear a presentation, I suppose.
Yeah, so I was already said, Lynn unfortunately is home in bed with not COVID, luckily, just a tonsillitis, but nonetheless, she's not feeling great, but she's watching on YouTube. So hi, Lynn, and congratulations. I'm super proud of you. You really deserve it. Okay, I'll do a quick run through of why we use these gold-silver core shell nanorods in lateral flow assays. So nanorods are very cool because they have really distinct optical properties, and you can tune them all the way from the near infrared to the visible. Quite often it's gold nanoparticles that are used, albeit them having less optimal optical properties really compared to silver. So if you look here at these electrical field intensity maps, then you can see that silver is much stronger compared to gold. So why don't we use silver? The answer to that is relatively simple. So silver nanoparticles themselves are very prone to aggregation, disintegration, and oxidation. So you can see here in the TM image, it looks like someone has taken a big bite out of it. That happens very quickly with silver nanorods. Additionally, there's not really a reliable synthesis of low aspect ratio silver nanorods with tunable optical properties in the visible spectrum. So what people have come up with is to use core shell nanorods with a gold core, a stable gold core, and a silver shell around it. Now, quite often these are actually made with, coated with very large polymers, making ligand exchange very, very difficult. So if we wanted to make them biocompatible or attach DNA or anything that would allow their assembly, that would be very difficult, if not impossible. So what Lynn came up with was this really simple method of creating these core shell silver nanorods that could be prepared at room temperature with any thiolated molecule as a ligand. So we use DNA here, for example, but any thiol-containing ligand really works. Now this makes them, these structures biocompatible, and controlled assembly is possible. So controlled assembly of nanoparticles on DNA origami has been done for a long time. You can make chiral structures, structures that can sense RNA in blood, for example, such as these nanorod structures here that came from our group as well. And we did a chiral assembly as well, and we could actually show, as you can see here, that the chiroptical response from these core shell nanorod assemblies is much, much stronger compared to the pure gold. So this basically means we could, in theory, if we use them, for example, like the RNA sensor in the switch beforehand, use them for very sensitive detection of RNA, for example. What Lynn and Max then, though, came up with is to use them in lateral flow assays because of the strong color response that we get. So lateral flow assays you've already seen in Lynn's pitch as a cellular strip and sometimes a casing, and the most prominent example are pregnancy tests, for example. However, for viral tests or any other diseases, these don't really exist because generally the concentrations of these in the bloodstream are too low. Now, most often gold nanoparticles are used in these strips, as you can see here with the red color, and they're gold nanospheres. And no matter which size of sphere you use, no matter what you do, the detection limit is 0.5 nanograms per milliliter, which is quite high if you want to detect early viral infections or something. And another thing is you're limited to a red color, because no matter what, the gold nanoparticles only have shades of red. So these gold-silver core shell nanorods that we have now, you can see here beautifully, cross the entire visible spectrum. And, as you can see here in this graph, have really, really strong extinction. So the thicker the silver shell, the more the color is shifted towards the blue, the stronger the optical response. What Lynn and Max then did with their partners microcoat is to test the nanorods in a lateral flow assay, so have the nanorods coated with an anti-FITC, and as it encountered the FITC on the membrane, the rods would accumulate and you could see a color. So as you can see here, did it with 2 different colors of nanorods, and the plan is to detect viruses but also cardiovascular diseases, because these strips are just so easy to use, so economical, and you get an answer within minutes. The stronger optical properties of these nanorods, we are hoping, is leading to increased sensitivity and gives us the ability to do multiplexing, so different colors at the same time, different viruses at the same time on the same strip, for example. So here's the sort of a first step where we did it with DNA, and you can already see, I mean, green is the most intense color, one of the most intense colors to the eye, so that also helps. But you can already see that even low concentrations of DNA here, which were detected, you can see on this strip, whereas if you use the gold nanoparticles in comparison, it's very, very hard to see them already. So we can already see an enhancement. And the hope is that later on we will get at least 10 times, hopefully 100 times signal enhancement for these strips for detection of viruses or cardiovascular disease markers. And that's already the end. Sorry that you had to hear it twice. Yeah, again, all the people that were involved in this work, and obviously thank you for your attention, and really sorry, Lynn, that you couldn't be here and take the award yourself. Thanks.
Thank you, Amelie, and apologies for the technical problems we had. Congratulations to Lynn out there, fantastic work. And now, finally, the final finalist, the first prize of the Nano Innovation Award 2020, the most innovative and excellent PhD research work that we've seen, goes to Dr. Bernhard Bohn. So Bernhard Bohn completed his thesis in the group of Professor Jochen Feldmann at the LMU in January 2020. The jury found that his work constitutes a technological breakthrough. He produced perovskite nanocrystal light emitters with an unprecedented quantum yield in a blue wavelength range. His results open a wide range of potential applications, as the technique allows to produce white light, all perovskite LEDs at comparatively cost-efficient technology. The success of the work is built on a very thorough scientific work and insight gained from understanding the light emission dynamics in perovskite nanostructures, and that allowed you to modify the nanocrystal towards the desired high emission yield. The findings have been published in Nano Letters in a remarkable article that was among the most read articles of this journal in the first year after publication. Congratulations. Okay. And we also do this. So the floor is yours. We'd like to hear more about your research. Thanks.
Okay, is the screen working now? Everyone sees the picture, yeah? Okay. All right. First of all, thank you very much. Yeah. Here you see the title of my PhD project, Exciton Dynamics in LED halide perovskite nanocrystals, recombination, dephasing, and diffusion. Today we actually only focus on the topic recombination. So actually, exciton recombination in LED halide perovskite nanocrystals. I've seen the other pitch videos, and it's really great and a great honor to have even reached the final round and now to stand here. as the last person. In my pitch video, I mentioned the Nobel Prize in Physics, which was awarded for the blue LED in 2014. This made white light LEDs possible. Since then, the journey of white light LEDs did not stop, and researchers also tried to find easier or cheaper ways to achieve white light emission. Recently, nanocrystals made of perovskite came up as an interesting material due to their properties, which enables tunable emission, cheap and facile synthesis, and high photoluminescent quantum yields, but also long-term stability. However, to have white light, you need all of these three colors. And the question is, are these four attributes already true for all of these colors? And we see where it's already true for the red and green spectral range, we don't achieve these properties in the blue. So the goal of my work was to find a tunable, efficient, stable blue perovskite emitter. And I will address now these topics one by one. So we will talk about tunability, efficiency, and stability. Before jumping into details, I want to explain the term perovskite nanocrystal. Perovskite is a crystal structure of the type ABX3. In my case, we used cesium, lead, and a halide ion component X. These crystals exhibit a typical octahedra structure, which is shown here. So this is a semiconductor material. Thus, emission, so sending out photons, is achieved by recombination of electrons and holes. So when an electron of the conduction band falls into an empty spot of the valence band, there is a possibility for light emission. Based on the band gap, so the energy difference, this light can have different colors. So in the end, this will decide if we have red, green, blue emission, or even colors which we cannot see. So generally, the emission can be tuned in two ways. First, via the material composition. This is shown here. Using iodide, we get red emission. Using bromide, we get green emission. And using chloride, we can achieve blue emission. But as you already see in this picture, the blue efficiency is very low, and also these nanocrystals are not stable. So this does not work proper enough. So the second way to achieve tunability is via quantum confinement. So by reducing the crystal size, and we start with a cesium lead bromide crystal, which is in the green range, as you see on the left, and we simply make the crystals thinner and thinner. We start with a cube, and as we go thinner and thinner, it will end up being platelets of different thicknesses. And this can be done with such an accuracy that we really talk about monolayers of this crystal structure. You see in the top, one monolayer is only 0.6 nanometers, and we can achieve just multiples of that. For example, 2, 3, 4, and so on. Now, the picture you see there on the top is basically, you can consider this is the smallest possible nanocrystal, only containing 8 octahedra, 1 cesium atom in the middle. And if you would write down the formula for that, it would not be cesium lead bromide 3, but it would be cesium and 8 lead atoms, as you see, and even more bromide ions. So actually, the formula is not ABX3 for very small crystals. So we thought about tuning the crystal size via this ratio of cesium and lead ions. So my colleagues and I, we came up with a synthesis routine where we have two precursors, one containing only cesium and one containing only lead. And by playing with this ratio, we could then achieve, and this is what you see here in this nice picture, basically samples of different color. And we have it from the blue, dark blue range up to the green range, just by playing with this ratio. And electron microscopy could confirm these thicknesses. So in the inset on the left and in the second and third picture, you actually see those platelets standing on their edges. So we could then measure their thickness, and we saw that we have multiples of the 0.6 nanometers, which we mentioned before. So we have, for example, here shown 2, 3, or 5 monolayer samples. Now let's take a look at the actual optical properties in detail. Here we see the PL spectra of several samples of different thicknesses, and you see this tunability throughout the blue range into the green, basically from dark and sky blue towards green. Every peak is quite narrow, and we don't have overlaps between the samples, meaning that each sample really contains only millions of basically platelets of the same thickness. Now when we look at the absorption spectra, this was very interesting to see at the first time. What you see when you look from the bottom to the top, so from cubes towards thinner platelets, a peak rising up at the absorption onset. This is a so-called excitonic peak. And what we observe is basically a transition from a 3D to a 2D material. And as we decrease the thickness, the influence or the role of excitons become more dominant. So this was a word I also mentioned in my title. Excitons are bound electron hole pairs. So in these nanoplatelets, electrons and holes are not free, but they are rather bound and stay together, which is also beneficial for emission. So this is the tunability which could be achieved. Let's next talk about efficiency. To be honest, when we first measured the quantum yield of these samples, it was rather disappointing. The thinnest nanoplatelets, indicated on the right by 2 and 3 monolayers, only had a quantum yield of around 10%. This is not sufficient for reasonable applications. And we took a closer look at this, and we thought this might be due to surface defects. This is indicated in the center. So there are some defects, some atoms are missing, and in these errors, you can have recombination without sending out photons. Now, we were kind of also lucky, that's also needed sometimes. We found that by adding lead bromide, we can actually repair these. So we call this the surface trap repair process. And after the repair process, we measured the PL again. You see this quick rise, arrows pointing up, and now we had efficiencies between 50 and almost 80%. Now this was a reasonable value. This were, at that time we reported it and published it, the highest efficiencies for emission of blue perovskite crystals. So let's take a look at this model. Whenever we measure a spectrum, we don't do it for a single crystal, we actually measure thousands of crystals at the same time. So you would always measure some crystals which have a high efficiency, some have a lower one, and as indicated here at the beginning, before we do this repair process, we have probably many dark gray platelets which contain defects, thus they are not very efficient in their emission properties. After the repair, we have mostly a dominant contribution of enhanced bright platelets, which mainly do recombination via sending out a photon, and this could also be confirmed by looking at time-resolved spectroscopy, where then the decay curves become more mono-exponential. As a quick add-on, I want to show you that putting lead bromide to the before prepared sample does not change the absorption at all. This is shown on the left side. So the absorption spectrum stays the same, only that the PL gets enhanced. In this example, I think we see the 2 monolayer sample where it's almost enhanced by a factor of 8. And also we tried to add different combinations besides lead bromide. So we also added other chemicals which only contain bromide. Also there we saw an increase in efficiency. However, only using lead and bromide, which are in the crystal anyways, led to that strong increasement. So we talked about tunability and efficiency. So we're coming almost to the end. We quickly talk about stability. Here we showed that by the repair process, also the long-term stability over 10 days could be improved. You see the first panel on the left, where we don't do the treatment. Compared to the initial black curve, after 10 days, we have a drop to around below 70%. It also gets broader, meaning that the platelets continue to grow, they stack together. But if we do the surface trap repair, which is shown on the right side, after 10 days, we have a slight decrease, but the shape stays the same, and these were not protected, so they were just basically standing in the lab for 10 days, and so this was a quite good result. And I also want to show you how they behaved under strong UV light emission. Even after several hours of strong illumination, the efficiency stayed between 80 and 90%, which was quite good, because other platelets or previous samples were destroyed within a few minutes. And now, basically, as the big highlight, and also why we're calling now today the Innovation Award, we also were able to build a proof of principle device in a collaboration, and we actually built a blue LED using this material. We see here a very sharp peak in the blue range, and also a picture of it, such that you can have an idea how this looks like. So summing up, we achieved a tunable emission, high quantum yields, and also the long-term stability, which then put together resulted in this small proof of concept experiment. Like, it's a small step towards closing the blue gap, and I'm very curious to see how this develops and if perovskite emitters will be used, or if you can buy them at the store at some point in time. But with that, I'm coming to the end. You find more information on this in the publication which was mentioned before, or also in my PhD thesis. And then I want to use also this possibility here to say thank you. First, I want to say thank you to my supervisor, Professor Feldman, without whom this would not have been possible, who supported me during the last years. Then, of course, my family, I think they're watching now. Probably my grandmother is the first time on YouTube, so it's always a highlight. Thanks to all my former colleagues. I will not mention anyone in specific, I mean all of you. Thank you to Marius Fischer and to Nicola Kerschbaumer. And yeah, thank you to Zenz also for always making such excellent events possible, not only today, but also throughout the year, and also especially now this year. I was very surprised to see what's possible even in the Corona crisis. Thank you.
Thank you very much. It's an impressive work. The thank really is to all of you that contributed, and I wish that everybody out there who's listening should applaud now for the finalists, for all the applicants, and also those that contributions that we have not seen. And with this, I'd like to give over to Dieter.
My main job is to say thank you for the spin-offs who really give the nice prize to encourage the next generation. Congratulate all the winners, and actually, if you would like to come up here again for the final group picture, it would be great. Thanks to the jury, and thanks for Susanne Henning and the whole Zenz team to organize this. It's really been a great event, and we are looking forward to next year's awardees. So please be encouraged to apply. Hopefully, we can do it in real world with all the people again. Let's try to keep the distance as much as we're legally capable to do.
Okay, good. Not too much. Okay.
So, congratulations. Thanks for all coming. Thanks for the great event. And that was the Zenz Nano Innovation Award 2020.
Thank you.
See you again next year.
Okay, thanks.
Congratulations.
Bye-bye. Ciao.
Thanks for coming.